in this lecture we are going to continue looking into the stability analysis, like different methodologies to do the stability analysis. So, basically we are going to focus on something called, like, this has already been taught in the lectures done by sir. So, and we are also looking to how to draw these plots etc., from how to draw polar plots, what is the polar plots, and how the polar plot can lead to the stability criteria plots etc. So, that is what we are going to look into this lecture. Starting with what is the polar plot. Basically, like, if you can remember from the lecture sir has taken, so we have S plane and we have this Fs plane, where we map every point in the S plane to the Fs plane, where this is like here it is a G of S plane, it is a G of S plane here. So, basically we map this. So, one way to understand how this mapping works is to represent things in polar coordinates. See, this is basically a complex plane. This is basically a complex plane. A complex number can be represented both in rectangular coordinate system as well as the polar coordinate system. So, basically now we will start looking into how to get these things. So, one thing we we ask is, like, okay, we will start at this origin point, okay, and then we will increase the value, of omega, and then you will see what happens. Basically that is what we are going to do. So, basically we will start at omega equal to 0 and then see what happens, and we will see at omega equal to infinity what happens. So, that is what we are going to see what happens. We will not go into detail of how these things are, but this is just to get an intuition of how these plots come. Basically we are expecting you to use MATLAB to get all these plots, but still, like, we will look into, like, why how these plots come from a very from just some for getting some intuition what exactly this, how we see how we can easily get these figures is what we are trying to focus. So, now when we have omega equal to 0, there is angular frequency equal to 0 and angular frequency is equal to infinity. Basically we are again interested in two things, right. One is the magnitude modulus of j omega, and other is the angle of j omega. So, when we said this is the in polar coordinate, this is the r and this is the theta, right. So, that is what we are trying to find out, and then once we know this, we can actually approximate this plot. See, this plot can be drawn in a more accurate fashion by considering few more points, but still, like, for now we will stick on to this idea. This is just to get an intuition of how we have to start doing all these things. That is what we are trying to do. So, basically what we are going to do, we are going to have the complex number g of j omega, which is nothing but 1 by j omega plus 0.25 and j omega plus 0.005, right. So, 0.005. We have 0.005 and basically, like, if you can find the magnitude of g of j omega, then what it will become, it will be nothing but 1 by root of omega square plus 0.25 square into in the denominator into root of omega square plus 0.05 square, right. So, this is what you get in the mod of j omega. So, now we will substitute the values of omega equal to 0 and see what happens. When omega equal to 0, what it becomes is, it simplifies to 1 by 0.25 into 0.05, right. So, that is what the 0.005. So, that is what it simplifies to. So, and this value you substitute here. So, 1 by 0.25 in by 0.005 is what the value you will get, say, let us call it, say, A for now. That is what you will get here. And what is the angle? Clearly when omega equal to 0, this is a positive constant, that is no, it is a real number and it is a positive constant. So, that is the angle is 0. So, basically here the angle is 0, right. So, just see, if you just substitute in g of j omega equal to 0, the j terms vanish. So, basically there is no imaginary term in that. So, what you have is 1 by 0.25 into 0.005, which is just a real number and a positive number. So, positive number means the angle is 0. So, that is what we have here. And when we say omega equal to infinity, what we have omega equal to infinity in sense the same mod of g of j omega we take, and that is nothing but 1 by root of omega square plus 0.025 square plus root of omega square plus 0.05 square. And if you substitute omega equal to infinity, basically what happens, it becomes like 1 by infinity form, which is nothing but 0. So the magnitude is 0 when the frequency is very high, infinity. And now if we substitute for angle, let us see what happens for angle. Angle of j omega is nothing but what, tan inverse minus tan inverse omega by 0.25 minus, so because it's a pole, it's a denominator, so we have the minus tan inverse, so minus tan inverse omega by 0.005, right. So if you substitute omega equal to infinity, what happens, tan inverse infinity is pi by 2, so pi by 2 is 90 degree, so minus 90 for this term and minus 90 for this term, so basically it becomes minus 100 degree. So when omega equal to infinity, this becomes minus 100 degree. So basically what we have done is, we have taken the extremes, when the angular frequency is 0 what happens, and when the angular frequency is infinity what happens. What happens in sense, what is the values of the magnitude and the phase, that is what we have got in this table. And with this table we will try to draw the a g of s plane and see how it behaves. Okay. So basically if you can remember from your schooling or something how to represent the complex numbers, we basically tell that that this is the imaginary axis, j omega axis, and this is the real axis, right. So this is the real axis sigma axis, and on the this is the j omega the imaginary axis, and this is 0 degrees, okay. And we take anti-clockwise as positive and clockwise as negative. Let us now look at clockwise basically. So this is like minus 90 degree, and this side is minus 180 degree, and this side is minus 270 degree, right. So this is what we look. So in clockwise, it's a usual convention that we do take anti-clockwise as positive and clockwise as negative. So here we take in the clockwise direction, we count in the clockwise direction, so we put the minus sign. So minus 90 degree, minus 100 degree, and then minus 270 degree. So this is what we have studied. So now let us plot all these points and then see how this graph will come. So that's what we were that's what we should get the same graph that we have got using MATLAB. So basically what we can do, when omega equal to 0, so when we will start with omega equal to 0, that is called as a point omega equal to 0, and this a value is 800. If you can find this value, I think it will turn to 800. That is what I can see from the graph, but yeah, you can calculate by yourself and see if it is close to 800. So and this one we will start at 800. So on the real line, since this is a real number, right, a is a real number, it had no imaginary term. So basically we are marking that point on that real line. So this is 800, and the angle is 0 degrees. So this is the 0 degree line, 0 degree. So basically you can even forget the angles and then say there is no imaginary part and it is a real number, positive real number. So I am just going to mark 800 comma 0, where 0 there is no imaginary part on. So anything, you can either use the concept of angle and then plot this point, or you can just use the j equal the coefficient of j is 0, so there is no imaginary number. So this is 800 comma 0 point. So anyway, this is the point that we will get when omega equal to 0. And then when omega increases, basically what we can see is the angle, this is the qualitative thing that we are interested in seeing, okay. The magnitude decreases to 0, the magnitude decreases to 0, and the angle actually changes from 0 to minus 100 degree. So basically if you can just plot here and then just look, we started somewhere here where we had some value of magnitude and the angle was 0, and then what happens towards when omega keeps on increasing, what happens, the magnitude keeps on decreasing. So if you see here, if you can draw a circle like this, so this is a, this is a, everywhere the circle is of the same radius, right. But what happens as when omega increases, at omega equal to infinity it is 0. So basically when omega increases, this should decrease. So this decreases, and then the angle also is changing from 0 to minus 180 degree. So this is minus 180 degree. So basically it comes, and maybe I will remove all this, yeah, now this is better. So magnitude decreases and also the angle also changes, it changes to minus 180 degree. So towards going to 0, the angle becomes close to minus 180 degree. So this is how you draw the qualitative plot. So when you mark this arrow to say that okay omega is increasing or it's changing from 0 to infinity in this way. So this is what you mark here. So this is what is called a polar plot. So why it is called polar plot, because it is drawn using this polar representation, the magnitude as well as the angle, etc. So this is a easy way of drawing, and some interesting things, to be more accurate, what you can do is you can try to see at what point it crosses the imaginary axis. So like if I ask you like at what point it will cross the imaginary axis, basically what you can do, you can take this term and then you can say this term's real part must be 0, right. So if on the imaginary axis the real part is 0, so you can equate this term's real part is equal to 0 and then find what is the frequency at which the real part is 0 and then find this point and do things. So all these things can be done for getting a more accurate representation of how it looks like, but this is the, we are just trying to look into how the qualitatively we can try to draw in a quick way of something without using MATLAB. So this is how you draw the figures, and this is called a polar plot. So we will go through one more example so that it makes things clear, but this is the idea. You best start with omega equal to 0 and omega equal to infinity, mark the extremes and then use the magnitude and the angle to draw a plot, and that plot is called a polar plot. Okay. So yeah, and so what this polar plot actually but we when we okay, I'm still not going into detail of this, but I will just tell you for the sake of intuition. So when we take from the S plane to the g of S plane, so what this polar plot says is when I change the omega from 0 to infinity is what it says, right. So now can I go around like this when I change the can I go around the S plane by a big orbit, and then can I still continue to do the closed contour like this from omega minus infinity to 0, can I complete the cycle. So what basically happens in g of S figure is, suppose we have add this figure, okay, what basically will happen is this for the portion that is like for the completion of this, what happens is basically this becomes the mirror image of that. So yeah, this has to be the mirror image of it, yeah. So this will become the mirror image of it. So basically you can intuitively feel like okay, this and this line or this is just a minus, like 0 to infinity omega changes, and this is minus infinity to 0 omega changes. So basically the angle alone changes for every omega, and then this at r equal to, this is like an infinite radius when you are actually covering the entire S plane, when you go via infinite radius, and that actually boils down to a point here. So we will, let's not go into detail, but what you need to take from this slide is like okay, I have drawn the polar plot. If you want to extend it for 0, not only to 0 to infinity but also from the entire S plane, if you want to go in a contour in clockwise direction and then come back, the Nyquist plot, what happens basically is it is the polar plot with its mirror image. So that is the thing that you have to remember, it is a polar plot with the mirror image. So you draw the polar plot and draw the mirror image of it, and what you get is the Nyquist diagram. Okay, that is something that you have to take care of it, and you can just substitute and see if you are really interested, curious to know like what exactly happens, how this became the mirror image. It's not a very tedious calculation except things, but you can just go and see like this. You take a infinite radius in the S plane, and what happens when you take an infinite radius that boils down to a point or something. So that's what you will get it. So and okay, when we did this border plot etc., like we were talking about this gain margin, phase margin etc., right. So interest might be like okay, from this polar plot or from this Nyquist diagram, I still should be able to have a way to figure out what is this gain margin, what is this phase margin etc. So if you but the thing is like it's very simple, like the same concept, the same ideas that we are using in border plot, the same thing we are going to apply here. So if you can recollect what exactly we said when about the gain margin and phase margin in border plot, what we said was we had a magnitude plot and we had the angle plot, and then we said that the angle was decreasing and then the magnitude was also decreasing, and at the angle of minus 180 degree is when we get the critical frequency, because that is the thing then when we get the in phase sine waves, all those things. So, basically that is the critical frequency we get. So, this is the omega c, and we actually mark we actually see what is the amplitude of, what is the magnitude of g of j omega at that point, and we said if this amplitude was, let's say, some m value, what is the multiplicative gain, that is m into say k, what is the multiplicative gain k that we can have, so that the multiplying it will become 1. So, k is nothing but 1 by m, so that is what we add as the multiplicative gain margin, or in decibels what we said, what is the additional decibels, or because when you take the log of it, it becomes like addition. So, 20 log m to the base 10 plus 20 log k becomes 0, because log of 1 is 0. So, then we say okay, if I know this m value, what is the gain value, what is the decibels, that is what we have to add, so that we get 0 here. So, that is what we say the gain margin in decibels. This is the gain margin in decibels, and this is the gain margin in multiplicative form. Okay. So, and again, like, but still the idea was the minus 180 degree, right, minus 180 degree, what was the frequency at minus 180 degree, and what was the magnitude at that frequency, at the critical frequency, that frequency at which the phase was minus 180 degree is called the critical frequency. So, at that what was the magnitude, that is what relates to the gain margin. So, same concept we apply here. So, when we said this is the minus 180 degree, you just need a polar plot for finding this gain margin and phase margin. So, that mirror image is not really required for this. So, but anyway, like we have mirror image, let us just forget for that for now. So, this is the real axis and this is the imaginary axis. So, and this is the polar plot, the bottom one is the polar plot. So, this is omega equal to 0 and this is the omega equal to infinity point. So, this is the omega infinity point. So, basically what happens, you draw a circle of radius 1, okay, that is first thing you do, and the next thing what you can do is like here at minus 180 degree. So, at minus 180 degree what was the gain? At minus 180 degree the gain is 0, right. So, it is going to the gain is going to 0, the magnitude is going to 0, basically m is going to 0 at whenever you get the phase is equal to minus 180 degree. So, basically it means that you can have infinite gain, right. So, basically if you want to say some m into k must be equal to 1 and then now m is equal to 0, because at minus 180 degree. So, if you can go back to the table what we have drawn, we said the minus 180 degree is got at the gain of 0. Right. So, the m is 0 here. So, here basically when m is 0, k is 1 by 0, which means it is tending to 0. So, basically it is like an infinite value, very high value, you can say very high value or a very high value, that is what you say here. So, this system is from gain margin perspective, this has a infinite gain margin. So, you can add any gain to system, still the system will be stable, that is what you can say from here. And then with regard to the phase margin, so when we what is the phase margin? Phase margin is like when I have a magnitude of 1. So, now I shift the question and I ask, okay, I have a magnitude of 1 here and then I have the phase plot here. So, what is the shift I have to do in this phase plot? Okay. So, what is this is the minus 180 degree line, somewhere I will draw this here. So, what is the shift I have to do to this phase plot? So, that I shift like this, by what angle it has to shift, so that this system will become unstable. So, which means that the angle at which m was 1 was equal to minus 180 degree, was minus 180 degree. So, that is what. So, at magnitude equal to 1, what is the angle I have to decrease, or what is the lag I have to introduce, so that my angle becomes minus 180 degree. So, that angle was called the phase margin, right. So, if you can remember phase margin, what is the angle that I have to add, so that my my final angle at the magnitude of 1 is becoming minus 180 degree. So that is what we set the phase margin. So the same thing what we can do is we can draw a circle of magnitude 1. So this is the circle of magnitude 1. So at this point we will see what is the phase. So this phase is somewhere between somewhere like this is 90 degrees, so and this is like little more than 90 degrees, so it is 14 degrees here. So we can add 104 degrees basically to we can add 104 degrees to where the system will be system will still be stable. Like to make it unstable we have to add 104 degrees. So that is what it says, the phase margin is 104. So that is how you calculate the phase margin. So the phase margin, we again the same rule, we take the magnitude of 1, we fix the magnitude of 1 and then find the angle, and then we say by what angle we have to add, so that the angle becomes minus 100 degree. So that is what, so here the angle is somewhat say minus here you take the what is the angle value, say theta, and then you say minus 180 degree minus this theta plus what angle you have to add, so that this becomes minus 180 degree. So that is what you add, and you find the value of angle here. So this is how you calculate the phase margin and gain margin from the polar plot or Nyquist plot. So that is what you got to remember. So just do it once, it is a very simple concept. If you understand the body thing, the same concept you apply here. So basically you ask only 2 questions. You ask first question like at minus 180 degree we call it as critical frequency, and at that critical frequency what is the magnitude, and by what scalar I have to multiply this magnitude so that I get the gain of 1. So this is the gain margin. And what is phase margin? We take the magnitude as 1 and then see what is the angle, and then we say by what angle we have to by what phase lag we have to introduce, so that this becomes minus 180 degree. So that is the phase margin thing. So that's the same thing you do here. So that's pretty much same thing. So here another example here. So this is the polar plot and this is the Nyquist diagram. So if you can see here, this if you draw the polar plot and then draw the Nyquist plot, like this becomes like very easy to draw, right. So this is like you just draw, okay, we will just draw it basically. So maybe this may be a good thing to draw because this looks very interesting shape, right. So so now we will say magnitude of, again omega equal to 0, what happens, omega equal to infinity, what happens to magnitude and then angle. So these are the 2 things that we are going to draw here. So at omega equal to 0 what happens, this becomes minus 5. So at omega equal to 0 this becomes minus 5 by 5 into 6. So this becomes like 1 by 6 basically. So this is 1 by 6, and what is the angle? Angle, it is a negative number, real number, so it is minus 180 degree. So remember a negative number has a phase lag of minus 180 degree, okay. Phase of minus 180 degree, a lag of 180 degree, so is what we say. So at omega equal to infinity what happens? At omega equal to infinity what happens? Substitute, if you substitute this, basically what happens is this becomes like still if you can substitute, you can take the magnitude as root of omega square plus phi square by omega square, root of omega square plus phi square into root of omega square plus 6 square. That basically will give, if you substitute limit s tends to omega tends to infinity, what basically happens is it will come of the form of 1 by some infinity limit, it will come as limit omega tends to infinity 1 by omega form, which is nothing but 0. It will come as some limit omega equal to infinity 1 by omega form, which will become 0. So this is effectively 0 here. And then angle, so at omega equal to infinity we have mod of magnitude is 0, and if you see the angle, basically what you have is we have tan inverse omega by minus phi minus tan inverse omega by phi minus tan inverse omega by 6, and when you substitute omega and remember, like this is a complex number form, and if you want to find the angle here, like if you could draw this, basically it means that this is in this quadrant, right, minus phi comma omega is somewhere in this quadrant when omega is tends to infinity. So basically if you, whatever angle you get, you have to basically you will get the angle somewhere here, So this and this are symmetric when you take the tan inverse. So basically what you have to do, you have to plus 180 degree here, so that you shift it back to this quadrant. So if you could refer to the complex number things from your school textbook, you will understand like why we need to shift this angle here. So basically and then we substitute omega equal to infinity. So then what you have is like basically we have minus 90 degree, because tan inverse minus infinity is minus 90 degree plus 180 degree, and then minus 90 degree and minus 90 degree. So what it turns out to be is nothing but minus 90 degrees. So this is what you get as minus 90 degrees here. So this thing quadrant thing you just can recollect from complex number thing, how to find the angles of complex number. So basically what you can imagine is if you have something like minus 3 plus 4j and 3 plus minus 4j here, and minus 3 plus 4j here. So if you take the tan inverse of if you want to find the angle, you will basically get tan inverse of 4 minus 4 by 3 right here, and this is nothing but tan inverse of 4 by minus 3. So both are like magnitude, the angle wise they are the same thing, but you can clearly see that this is clearly an acute angle, and this is nothing but just opposite to this. So basically this plus 180 degree is what will give this angle. So that is why this additional 180 degree we are adding it here. So basically we are now done with all the things that we are done with all the things that we want. So now we will go and draw the plot and see whether it works fine or not. So now with this what we have is at omega equal to 0, okay, the magnitude is nothing but 1 by 6, which is coming around like say 0.16 something. So this is what you have as a starting point, the amplitude here. So this is nothing but 1 by 6, okay. So and then what we have is like as and when omega increases. So when omega increases, what happens, the angle also increases from minus 180 degree to minus 90 degrees, and then the magnitude also keeps decrease. So here actually it is little more interesting, because you need to have more points here, because you have a 0 and 2 poles. So you need, if you take more points here, substitute more points like middle values of omega here, you can basically find that this graph shows that the amplitude is increasing at first and then it decreasing, and then it goes to minus 90 degrees. So at the end point you can see it is this minus 90 degrees. So basically what you have is this is what the polar plot you have, and then you take the mirror image of the polar plot, you will get the Nyquist plot. So that is what you are going to have it here. So in the previous lecture we asked this question like body plot was not able to capture whether this system is stable or not, but this system was really stable system, but body plot said this was having a negative gain margin, and then it was probably we felt it was not stable, but still with experiments we found that we put a P controller and then we proved that it was a stable system. So then we now can Nyquist plot, Nyquist stability criteria help us with this, okay. So that is what we are trying to ask the question. So now we draw the Nyquist diagram of the Nyquist diagram. Similarly construct a polar plot and then construct the mirror image of the polar plot, so that you get the Nyquist diagram. And then what you need to do, basically you need to just find out some values, right. You have to first find number of clockwise encirclements about the point minus 1 comma 0, right. So this is the first thing that you have to find, and then like remember you are drawing the Nyquist plot for GC, which is like the open loop transfer function. So what we call this open loop transfer function is, if you have a loop like this, you have a G, you have a controller C, and then you have a process G, and then you have a feedback H. So this is what you have. So basically what you draw for which you draw the Nyquist plot is nothing but C into G into H. So this is the transfer function, say you call it some T. This is what you this is for this is what you will draw the Nyquist plot. This is all the open transfer function, but the closed loop transfer function is nothing but Cg by 1 plus Cgh. So this is the closed loop transfer function. So remember, this is open loop transfer function, this is a closed loop transfer function. Okay. So, now coming back to our question, number of clockwise encirclements, clearly this is not encircling anything. So, this is not a circle at all, it is not encircling anything, this is just going like this and this is just going like this. So, definitely number of clockwise encirclements is 0 and number of poles on the right hand side of the S plane is also like p is also 0. So, you get z is also 0, which means clearly the system is stable. That is what this also says, the system is stable. You can also use MATLAB to know that system is, you can just ask for whether the system is stable or not. You can ask for the stability margins, just click on the Nyquist diagram and then see the options, play with this and MATLAB, and then you will be able to get this. So, in unstable, let us go for unstable system. Okay, let us take this system and then let us draw the polar plot. So, this is the polar plot, and then you can try to draw this polar plot. I am not going to like try work out this, but you can just draw this. Basically what you need to do, you need to just put omega equal to 0, omega equal to infinity, and then just check whether the endpoints are matching, etc. See, this is not 0, this comes down and then goes back, so it is minus 90 degree. So, it goes to minus 90 degree and magnitude goes to 0, and here the magnitude is somewhat what it is greater, somewhat approximately 16 or something, I am not sure. So, that is the magnitude you have, and then that is the angle you have. So, this is what you will find from this, but you can just play up like express this in terms of magnitude and an angle, and then just substitute omega equal to 0 and omega equal to infinity, and then see what happens. So, basically you get this polar plot, and then you take the mirror image of the polar plot, you will get the Nyquist diagram. So, now minus 1 plus j0 point is here, that is a clockwise encirclement, which is the big thing, right. If you can see the big thing is a clockwise encirclement. So, n equal to 1, okay, n equal to 1 is the clockwise encirclement, and there are no poles on the right hand side of S plane of the open loop transfer function. So, p equal to 0, and hence what you get, you have this equation n equal to z minus p, right. So, when n equal to 1 and p equal to 0, you get z equal to 1, which means that in the closed loop transfer function there is a pole, one pole on the right hand side of the S plane, which means the system is unstable. So, what it means, if there is a pole on the right hand side of S plane, what it means basically is you get e power some positive constant into t, say lambda t, and then this is going to get as time increases, this is going to, amplitude is going to get increasing so much. So, that is what you are going to get. So, this is the this is one example of unstable systems. So, remember this is the encirclement that you have, the big one. So, this is the encirclement that you have. So, this is the clockwise encirclement, and this is not an encirclement. Yeah. So, yeah, we are coming to the end of this Nyquist stability and things, but like we have just done some very few examples. So, you may actually use MATLAB to get more examples, and then just create some random transfer functions, create a system with time delay. So, basically in MATLAB, if you want to give time delay systems, in MATLAB, basically what you need to do is you have to put s equal to transfer. So, this is just to tell that that you use this variable s for transfer functions, and then you say some transfer function g equal to k by 1 plus say tau s into exponential of minus d into s. So, if you can do this and then you put the Nyquist here. So, if you can plot this Nyquist graph and then see, substitute various values of k and tau and d, and then see what actually happens when system goes unstable, what are the effects of dead time on stability. So, these are all something that it will be interesting for you to yourself try and learn, and that will be like making things more interesting. So, yeah, with this we have come to the end of the lecture on Nyquist stability analysis. Thank you.